If you clicked just for the Pokémon, this is your warning. This is 100% a math video. But if you have a passing interest in mathematics, you might still get a kick out of it. You see, this problem was on the 2023 IMO shortlist. That's the International Mathematical Olympiad. It's basically the World Championship of high school mathematics. Each year, a bunch of countries send their brightest students to some agreed-upon location to battle it out over 6 math problems. This being on the short list means it was almost selected to be in the competition, although it wasn't. But it's still a really good problem, and as far as high school math problems go, it's pretty darn hard. But as IMO problems go, it's fairly easy. So let's read through the problem, and then I'll give you some additional context in case you don't know what a Pokémon is. It says, Professor Oak is feeding his 100 Pokémon. Each Pokémon has a bowl whose capacity is a positive real number of kilograms. These capacities are known to Professor Oak. The total capacity of all the bowls is 100 kilograms, and Professor Oak is distributing 100 kilograms of food in such a way that each Pokémon receives a non-negative integer number of kilograms of food, which may be larger than the capacity of their bowl, so a Pokémon's bowl might get overfilled. Then, the dissatisfaction level of a Pokémon who received N kilograms of food, and whose bowl has a capacity of C kilograms, is equal to the absolute value of N minus C. That's just the absolute difference between the bowl's capacity and the amount of food Professor Oak filled it with. If the capacity was 10 and Professor Oak filled it with 5 kilograms, the dissatisfaction level would be 5. If he filled it with 15 kilograms, same thing, the dissatisfaction level would still be 5. We're asked to find the smallest real number d such that, regardless of the capacities of the bowls, Professor Oak can distribute the food in a way that the sum of the dissatisfaction levels over all the 100 Pokémon is at most d. If you're wondering what a Pokémon eats, well, they eat a variety of things, among them being the Poképuffs. Yes, they're an indulgent lot. And if you're wondering what Pokémon even is, in the Pokémon video games, players take on the role of a sort of high fantasy Michael Vick. They go around collecting and battling cool and adorable creatures like Jinx and Grimer, for example. Now that you have that context, let's get back to the problem. There's a lot of important information here we need to make sure we're aware of. Note that the capacities of the bowls are known to Professor Oak. This means the strategy he uses to give the Pokémon food can depend on the capacities of the bowls, because he knows what they are. The food that he doles out to each Pokémon is a non-negative integer. That's also very important to note. This could be because he's distributing Poképuffs, for example, and perhaps each one weighs 1 kilogram, so he can only divvy them up in whole number kilogram amounts. Again, keep in mind the dissatisfaction level of a Pokémon just depends on how much food they received and how far away that is from the capacity of their bowl. It doesn't matter if they get more food than the capacity or less food, it's just the difference that's important. Other big picture details like 100 Pokémon and 100 kilogram total capacity are obvious, but those are a couple of the more subtle and easy to miss details. Alright, the reason this is a tricky problem at all is because of the capacities of the bowls, which are positive real numbers. It could be, for example, that the capacity of every single bowl is exactly 1 kilogram. We could write this as C1 equals C2 and so on, all the way up to C100, so all 100 bowl capacities are equal, and in fact, they equal 1. In this case, since remember, Professor Oak is distributing 100 kilograms of food total, he could easily just put 1 kilogram of food in each of the 100 bowls, and every Pokémon would be perfectly satisfied. In that situation, the total dissatisfaction level, which we may call lowercase d, is equal to 0. Every Pokémon's bowl gets exactly as much food as it can handle. This set of bowl capacities works nicely because they're all positive integers, but the big issue is that they don't have to be, so they could be a much less friendly set of capacities, like C1 equals C2 and so on. Let's say the first 99 bowls all have capacities of 0.5 50.5 kilograms. Remember, the capacities totaled up have to equal 100 kilograms, so in this case, C100 would have to be 50.5. This is certainly a less satisfactory set of bowl capacities to deal with. No matter how Professor Oak distributes the food in a situation like this, every single Pokémon is gonna have a dissatisfaction level of at least 0.5. That's because Professor Oak can only distribute food in integer kilograms, and every one of these capacities is exactly 0.5 away from the nearest integer. This means whatever that smallest real number D is that we're looking for, it's certainly at least 100 times 0.5, because no matter how Professor Oak plans to distribute the food, this set of bowl capacities would ensure every Pokemon has a dissatisfaction level of at least 0.5, so in total 100 times 0.5, or 50. To solve the problem, though, it's not sufficient to say that D is at least 50, we need to figure out exactly what D equals. Remember that in finding D, we're finding the smallest real number so that no matter what the capacities of the bowls are, Professor Oak can ensure the Pokemon's net dissatisfaction level doesn't exceed D. Now that we know D is at least 50, if we could show that D is also no more than 50, then the problem would be solved, and we would have that D must be equal to 50. This part of the problem is much trickier. To show that D is less than or equal to 50, we need to demonstrate a strategy for distributing food to the Pokemon, which ensures the net dissatisfaction will not exceed 50, no matter what the capacities of the bowls are. So then what's the best strategy we could devise for Professor Oak to distribute the food to the Pokémon? One simple idea you may have is that he should just round to the nearest integer for each bowl capacity. So, as you've no doubt gathered by now, we're letting Ci be the capacity of the bowl of the ith Pokemon, imagining we've numbered them 1 through 100. And perhaps if we just give the ith Pokemon the nearest integer to his bowl's capacity, we will have exactly the strategy we need. This is the notation which means nearest integer. So if a bowl's capacity was 0.9, this would round to 1. If a bowl's capacity was 2.3, this would round to 2. While this seems nice at first glance, it's not a coherent strategy. The issue is that from rounding up repeatedly, we may be unable to give the needed amount of kilograms of food depending on the bowl capacities. For example, imagine the first 99 bowls have a capacity of 0.9 kilograms. Then with this strategy, Oak would have put 1 kilogram of food in all 99 of these bowls, meaning he would have only a single kilogram left for the 100th bowl. But the capacity of the 100th bowl would have to be 10.9. That way, adding all of these together would give us a total capacity of 100. Remember, the problem tells us that the total capacity of all bowls is 100 kilograms. The issue here isn't so much that the 100th Pokemon is left pretty dissatisfied, but rather that this strategy isn't even possible in all cases. Like this one, for example. We don't have enough kilograms of food to implement the strategy in this situation. But that doesn't mean this is a bad idea. We have the right idea. We need to be distributing integers near the capacities of the bowls. It's just that rounding up presents this issue, so we should exclusively round down then. So then now, beginning to describe the strategy that actually will solve this problem, again we're letting Ci be the capacity of the bowl of the ith Pokemon. Step 1 of this strategy is going to be to give Pokemon I the rounded down capacity of the bowl. Whatever their bowl's capacity is, rounded down. That's what this notation is. It's the floor function, it just rounds the capacity down. So if a Pokemon's bowl has a capacity of 2.9, we're going to give them 2 kilograms of food, and not anymore. If a Pokemon's bowl has a capacity of 7, this would just round it down to 7, the nearest integer. If it's something like 8.2, it would round it down to 8. After doing this, a Pokemon's dissatisfaction could be pretty high. For example, a capacity of 1.9 would get 1 kilogram of food and have a dissatisfaction level of 0.9. However, since we're rounding down all of the capacities, once we do this, we're still going to have some food left, and so we need to distribute that intelligently to minimize dissatisfaction. Now, any Pokemon whose bowl had an integer capacity would have been fully satisfied. They'd get the exact right number. So let's worry about the Pokemon whose bowl's capacities had fractions. To this end, we need some new notation. We'll say let Fi equal Ci minus Ci rounded down. This means that Fi is the fractional part of the capacity of the bowl of Pokemon I. If the capacity is 2.4, for example, then Ci is 2.4, and this is subtracting 2, leaving just that 0.4, that decimal part, behind. We'll then suppose, without loss of generality, that F1 is less than or equal to F2, and so on all the way up to 100. This just means the way in which the Pokemon are numbered does not matter. It would be useful for us if they were numbered in such a way that the fractional parts of their bowl's capacities increase as we go from the first Pokemon to the 100th Pokemon. So, since we can, let's number them that way. So the fractional part of the first Pokemon bowl's capacity is less than or equal to the fractional part of the second Pokemon bowl's capacity, and so on all the way to the 100th Pokemon's bowl. This is useful because then, with that extra food we have after doing this, we know exactly where the extra food should go. It should go to the Pokemon whose fractional parts are highest, because those are the Pokemon who will have the highest dissatisfaction level after this first step of our food distribution. Just imagine one Pokemon whose bowl capacity is maybe 4.2, and then another Pokemon whose bowl capacity is maybe 6.7. After we follow step 1 of our distribution strategy, the dissatisfaction of this Pokemon would be 0.2, because he would have got 4 kilograms of food, but this Pokemon would have a dissatisfaction level of 0.7. Thus, it will be a better idea to give this Pokemon an extra kilogram of food to then bring their dissatisfaction level down to 0.3. Because this dissatisfaction level means that we gave 0.7 kilograms too little. So if we give 1 more kilogram of food, we'll be at a 0.3 too much, which is better. So again, we're saying we've numbered the Pokemon so that the fractional part of the 100th bowl is greatest, and then the fractional part of the 99th bowl is next greatest, and so on. Now, how many kilograms of food do we actually have remaining to give to these Pokemon with high fractional parts? Well, let's call that remaining amount of food R. Then it's easy to calculate. It's just 100, the total amount of food we began with, minus the sum of all the bowl capacities rounded down, because that's how much food we doled out. So C1 rounded down plus C2 rounded down, and so on all the way up to C100 rounded down. So that's 100 minus all of the food we gave out, but there's also another simple way to calculate the remaining amount of food, which is to add up all of the fractional parts of the bowl's capacities. Remember, the amount of food we have total and the sum of the bowl's capacities are equal. They're both 100. So by adding up all of the fractional parts we missed, some of these could be 0 if the bowl's capacity was an integer, but we can still put it there in the sum. If we add all of these up, we have to get the amount of food that we didn't give out. If we gave out 80 kilograms of food after the first step of our distribution, there would be 20 kilograms left, which must be entirely matched by an additional 20 kilograms of fractional bowl capacity. Okay, then with our kilograms of food remaining, what we're going to do is give an additional kilogram of food to the Pokemon whose bowls have the top R fractional parts. There's that part of the strategy written out. We're giving 1 kilogram of food to the Pokemon numbered 100, 100 minus R, and so on up to 100 minus R minus 1. Remember, we numbered the Pokemon so that from higher numbers to lower numbers gives us higher fractional parts in the bowl capacities to lower fractional parts. So these are the top R bowl capacities in terms of fractional part, which means those will be the Pokemon left most dissatisfied after our first round of giving out food. Now, this all comes down to showing that the net dissatisfaction level using this strategy is no more than 50. So then we'll let D be the net dissatisfaction level using our strategy. First, we need to add up the fractional parts of those bowls that didn't get an extra kilogram of food. That's F1, F2, and so on, all the way up through F100 minus R. Remember, it's the top R fractional parts that we gave an additional kilogram to. If F1 was 0.2, for example, maybe the bowl capacity C1 was 1.2, we would have given 1 kilogram of food to that bowl, and there would be a 0.2 level of dissatisfaction. To add up the rest of the dissatisfaction levels, we need to take those top R fractional parts and subtract each of them from 1. What's the dissatisfaction level for the 100th Pokémon? Well, it was F100, the fractional part of his bowl capacity. But then we gave him 1 additional kilogram of food, so now his dissatisfaction level is 1 minus F100. If his fractional part was 0.8, that's how much he was originally dissatisfied, but then we gave him an additional kilogram of food, so now his dissatisfaction level would be 1 minus 0.8, or 0.2. And this would continue. 1 minus F99, 1 minus F98, and so on, all the way down to 1 minus F100 minus R minus 1. So here's the total dissatisfaction level, which we're trying to show is no more than 50. We can simplify this sum a bit, because this part with those top R fractional capacities that got an extra kilogram of food, there are R of these total, the top R of them, and so we have 1 plus 1 plus 1 and so on, R times. We could imagine collecting all of those ones together, and it would just be R. Then we could write this as F1 plus F2 and so on up to F100 minus R, plus those R copies of 1 brought together, so just plus R, and then minus all of those fractional capacities. So minus F100 plus F100 minus 1, and so on. So then we've rewritten it like this, and actually R is a very nice term to have in this sum. Remember, we previously wrote R as the sum of the fractional parts of the bowl capacities. R is equal to F1 plus F2 and so on up through F100. This means that in R, there are all of these terms, F1 through F100 minus R, so all of those could be doubled because R has those, but then also R has all of these, so those would get canceled out because R has them as well. R has all of these fractional parts added together, but positive, so when we subtract it, they cancel out. At which point, all that would remain in this net dissatisfaction expression is 2 times this. F1 plus F2, and so on up through F100 minus R. Now, to solve this problem and show that D is no more than 50, we're going to need an inequality. So let's get an inequality going by using the arithmetic mean. What's the arithmetic mean of all of these fractional parts? Well, of course, it would be their sum, F1 plus F2 and so on, and then divide by the total number of terms, which is 100 minus R. It's the number 1 smallest part up through the 100 minus rth smallest part, so 100 minus R terms total. And we know that this average, this arithmetic mean, is certainly less than or equal to the average for all fractional parts total. Because remember this ordering they follow. These are the smallest ones, the first 100 minus R of them. So if we compare that arithmetic mean to the mean of the total for all fractional parts, it would certainly be less than or equal to that total mean. That mean, of course, is found by just adding up all 100 fractional parts and dividing by the total number of terms, which of course is 100. Of course, we need to get our D involved. How do we do that? Well, look at this numerator, F1 plus all the way up through F100 minus R, that's this. D is 2 times that. This is 1 copy of that, hence this is half of D. We could thus rewrite the left side of the inequality as 1/2 D, or D over 2, also with 100 minus R still in that denominator, and this is less than or equal to the right side. Then we can multiply both sides by 2 to cancel out this 2 in the denominator. Over here, 2 divided by 100 is 1 over 50. And we might as well also multiply both sides by 100 minus R. We thus arrive at this inequality. D is less than or equal to 100 minus R times the sum of the f's divided by 50. Remember, the 100 became a 50 because we multiplied by 2. By the way, if you're wondering about this being 0, 100 minus r, which would be a big problem, that's not possible. The only way this would be 0 is if r was 100, and the only way that could happen is if every single one of the bowl capacities were less than 1. That would mean they all get rounded down to 0, and so there's 100 kilograms of food remaining after our first pass of doling out food. That's not possible because if all 100 capacities are less than 1, then the total capacity is not 100, but it's got to be 100. So r is definitely not 100. Anyway, speaking of r, look at this. F1 plus blah de blah de blah up through F100, we know that's r. So let's go ahead and replace that with r. So this is equal to, this is r multiplied by 100 minus r divided by 50. Now look at this. In some way, these two factors are begging to be added, not multiplied. If we added them, those r's would cancel out. Is there any sensible way we could be adding these factors together? Yes, there is, which is to consider the AM-GM inequality. That tells us that the geometric mean of two quantities is less than or equal to their arithmetic mean. The geometric mean of two quantities is the square root of their product, so the inequality says that the square root of xy is less than or equal to the arithmetic mean x plus y over 2. The numbers x and y also have to be non-negative. Certainly that's the case in our situation, so we're good to go. We're applying this inequality to the two numbers r and 100 minus r. Thus, by the AM-GM inequality, we have on the left the square root of r times 100 minus r, and this must be less than or equal to the arithmetic mean of those two terms, r plus 100 minus r divided by 2. Of course, r plus 100 minus r is just 100, so this is 100 over 2, which is equal to 50. Okay, so the square root of this product is less than or equal to 50. Let's go ahead and square both sides, and thus we get that r times 100 minus r, which remember is in the numerator in our expression that's greater than or equal to d, r times 100 minus r must be less than or equal to 50 squared. All right, we're done. What is d less than or equal to? It's less than or equal to this, and we've just seen that the numerator, r times 100 minus r, is less than or equal to 50 squared. Thus, we can say that this is less than or equal to 50 squared divided by 50. Of course, 50 squared divided by 50 is equal to 50. And so we have that d, the net dissatisfaction using this strategy, is less than or equal to 50. Then, having established at the beginning that the net dissatisfaction could be made at least 50, no matter how the food is distributed, we've now also shown that following our very clever strategy, the net dissatisfaction level is no greater than 50. Hence, the only possibility which remains is that d is equal to 50. This is the smallest real number, so that no matter what the capacities of the bowls are, Professor Oak can distribute the food in such a way that the net dissatisfaction will not exceed this number. So that's a fun Pokémon algebra problem from the 2023 IMO shortlist. Let me know in the comments if you had any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, feeling arc to keep the cable cut and unsort the table. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.